Swayam Prabha. Digital India. Educated India.
Welcome. So, we are in module 11. In this module, basically we will discuss few things or few interesting things about finite element technology. One of them is actually locking. So, in this lecture, I will introduce what is shear locking. There are mainly two types of locking. One is shear locking, another is volumetric locking. So, I will introduce shear locking mainly. In fact, we have already, or I have already introduced shear locking in the Timoshenko beam theory. So, if you remember, simple shear locking for the beam element. Now, in this lecture, what I will discuss this shear locking for the one-dimensional beam element, that in during the thin limit or thin beam limit, the mesh locks. That we have also studied some of the alleviation or locking alleviation scheme like shear reduced integration technique and other things. So, consistent interpolation, for instance. And here I will just show with and also I will discuss the parasitic shear, which is known as the locking in or the Q4, that is 4-noded bending element or 4-noded bilinear element, where we have also see that this element is overly stiff element, and during bending it produces spurious shear energy. So, this also we will discuss what is the actually reason that mesh locks, and why we should be taking care, we should be while in discretization or while considering the element for a given problem, why we should keep in mind that this kind of element will have some specific behavior in specific deformation modes like bending. So, let us first discuss what is one-dimensional beam. That if you remember that suppose there is a beam element that I discussed in the previous module, that this beam, if I consider it's a beam element. So, this is x and y axis, this is node 1 and node 2, and if you remember that we were doing this kind of problem during, so this is theta 1, this is theta 2. So, theta 1 and theta 2 we can linearly interpolate. For instance, linear means first order Lagrange polynomial. For instance, W I can interpolate in this way, that is 1 minus x by L W1 plus x by L W2, and theta that is also 1 minus x by L theta 1 plus x by L theta 2. So, now if you remember that we have discussed this, that in case of a thin beam it will be Euler-Bernoulli beam, and theta is actually the slope of the displacement, that is for Euler-Bernoulli beam, that is or the thin beam. Basically here what I am referring is thin beam, that is the where the shear deformation is negligible, then theta must be equals to dw by dx. Now, if you do this, then dw by dx here from this interpolation, that is essentially constant, but which is, if you take the derivative of it, then that is W2 minus W1 by L. So, this is a constant, while your theta is a linear variable. So, element wise displacement derivative is constant, while the theta variable is linearly interpolated. So, this is an inconsistency which will actually create the bending energy to be 0 and the shear energy will be high, and this is for this reason the mesh will start giving the value, the discretization or the solution will start giving the garbage value as the aspect ratio or the thickness to length ratio that is growing in terms of increasing aspect ratios. So, another way to visualize it is if you consider simply a thin beam, and now suppose this is a Timoshenko kind of beam, and then we all know what is the displacement. So, if x displacement is u and y displacement is v, that is equals to w, that is then u of x y z, I can write that is y minus y theta of x. So, and v, that is x y z, that is your w of x. Then naturally the strains epsilon xx is del u del x. So, del u del x will be your minus y d theta dx. Now, epsilon y will be 0, and gamma xy, which will be non-zero because this is a function of y. So, del u del y and del v del x. So, naturally del v del x is dw dx minus theta x is your shear strain. Now, if you assume that again the constitutive relation, that is linear elastic plane stress and all those things, then you will have this sigma xx is your minus e y d theta dx, and sigma yy will be 0, and sigma xy, which is g into gamma xy, that is dw dx minus theta x. Now, here to match the shear stress profile of the beam, which is parabolic in nature for rectangular case, that is that's why we add some shear correction factor. So, this is also you have studied in mechanics. Now, if you look the strain energy, if you consider the strain energy, then the strain energy, there are two components. One is UB and one is US. Now, look, for thin beam, the shear strain energy must be going to 0, because there is the assumption of Euler-Bernoulli beam, that is shear strain must be equals to 0. So, naturally for this case, since our shear strain is non-zero, then there will be a shear strain energy. So, that is we also studied, that is half EI into your EI into d theta dx whole square. So, that is your bending strain energy. And what is the shear strain energy? Shear strain energy is again Ks G A by 2, that is, this is integral 0 to L, 0 to L. So, that is dw dx minus theta whole square dx. So, now if I consider the area is your B into H, and I, that is your BH cube by 12, then I can easily write this and constant as EBH cube by 24 0 to L d theta dx whole square plus Ks GBH by 2 integral 0 to L d theta dw by dx minus theta whole square dx. Now consider a simple cantilever beam with one element discretization. So what here I am trying to show that if you use linear interpolation for w and theta, what happens to the strain energies. So now suppose there is a cantilever beam and this beam is discretized with one element which is your P. This element is actually length L and you have two nodes, one is here, another is here. So here W1 is 0 and W theta 1 is also 0, but here W2 and theta 2 is non-zero. So now if I try to approximate with this, then my W2 which Wx, that is your x by L W2. Now theta x again that will be your x by L theta 2, right, because W1 and W2 are W1 and theta 1 are 0. Now if I substitute this in the strain energies, then what will happen? So first let us do the bending strain energy. So bending strain energy, that is UB, that is if I do that, then that is EBH cube by 24 into 0 to L d theta dx, which is actually theta by L. So that is theta square, theta 2 square by L square, that is dx. Now this if you integrate, then what will happen is that EBH cube into theta 2 square L by 24 L square. So that is EBH cube theta 2 square by 24 L. So now this is the bending strain energy. Now what happens to shear strain energy? Now shear strain energy, if I take this, that is Ks GBH by 2 integral 0 to L, your dw by dx is actually your W2 by L. So W2 by L minus d theta, so that is x theta 2 by L whole square dx. Now this is actually your Ks GBH by 2 integral, so 2L square I can take out, 0 to L. Now that is your W2 square plus x square theta 2 square minus 2x W2 theta 2. So that is my shear strain energy. Now if I take the integration, if I do the integration, what will happen? So let us see. So Ks is GBH by 2L square into your W2 square L plus L cube theta 2 square by 3 minus L square W2 theta 2. So that is my bending strain energy. Now if you look carefully, that your bending strain energy is EBH cube. Now if H is thickness becomes less, then this energy UB is UB is comparatively low compared to the shear strain energy because of this GBH, because it has only H term, while in the bending strain energy it is H cube, so it will be much more less. So this actually creates the problem. Now if I for this problem, if I write the potential energy, then my potential energy will look like this. For instance, my bending strain energy is EBH cube theta 2 square by 24L plus KSGBH by 2L square. Now this is multiplied by your W2 square L minus L cube theta 2 square by 3 minus L square W2 theta 2. That is your strain energy, minus P into W2 is your work done. So that's the potential energy. Now if I just follow the minimization of potential energy with respect to theta 2 and W2, that's what we did for Rayleigh's earlier. So then we can calculate W2 essentially. So d pi by d theta or dW2, that is equals to 0, and d pi by d theta 2, that is equals to 0. If I do that, then what will happen? Because first equation, that is d pi by dW2, that is equals to 0. That means your EBH, this term will not be there. So now this term will only be there. So KSGBH by 2L square. Now this is your 2W2L, and here only, that is L square theta 2, that is equal minus P. That is your first equation. So equation number A. Now similarly, d pi by d theta 2, if I do, then that is your here EBH cube theta 2 square. So theta 2 square will be theta 2 by 24L, right? And then here KSGBH by 2L square, that is your here this will be there. So 2/3 theta 2 L cube minus L square W2. So solving these two equation, so that is equals to 0. So this is second equation. So solving these two equation, I can find out easily what is my W2. So from here, from equation B, if I do some manipulation, then what I will get is something like this. So I have done this manipulation, and if you see that this manipulation is something like this. Theta 2, if I just substitute from B, if I do this manipulation, then theta 2 is KSGBH by 2L into W2 by 1 by EBH cube by 12L square plus KSGA by 3. So here essentially, if I substitute BH equals to A, then I can write this again, KSGA by 2L into W2 1 by your EAH by L whole square EA by 12 H by A whole square plus here it is BH, so K is GA by 3. So this is the theta 2. Now once I compute the theta 2, if I substitute, so substitute theta 2 in equation A gives me W2. So W2 will look like this. So which is I am not just doing this calculation, so you can do this calculation to find out what is the whether these expressions are correct or not. So that is H by L whole square plus 4KS GA by E into H by L whole square plus KSGA into PL by KSG. Now this is my W2. Now if you see that this expression for W2 essentially depends on the H by L ratio. So H is the thickness of the beam. So now so if I thickness of the beam means the height, this is H actually. So this is actually the H. Okay. So now here if I say that my H by L ratio, that is very H by L ratio is close to 0, that means very thin beam. So H by L ratio is much less than 1. So then I can consider it 0. So if I consider, that means then H, if I consider H by L, if I approximate as 0 or very less value, that is very thin beam, then what will happen to my W2? My W2 will contains only 4 PL by KSGA. So you can see that if I again take that KS is 5 by 6, that is rectangular beam. For instance, if I take KS equals to 5 by 6, then this will look like 4.8 PL by GA. So if you look this deformation is not at all a bending deformation. So this is because there is this term, the bending contribution, actually goes to 0. So that's why this when the thickness becomes very less, or it is a thin beam, or specifically the H by L ratio, if it is very low, then essentially this represents only shear deformation, and there is no bending contribution in it, which is incorrect, because in Euler-Bernoulli beam theory, what we have understood is that shear deformation is negligible, while bending deformation is the prominent deformation mode, or bending or the flexure is the prominent deformation mode. So that's why if you use this kind of linear interpolation for theta and W, this will lock essentially, and it essentially depends on this H by L ratio, how this deformation will actually come out. So this is the main reason of the locking, or specifically the shear locking. On the other hand, if H by L ratio is approximately equals to 1, then you will get the shear deformable beam, that is your E plus 4KS GA by E plus KS GA. So that is your shear deformable beam, so which will actually will have the bending as well as shear deformation contribution. So that means thin beam, so this is for thin beam, and this is for thick beam. So this is the main reason why this kind of linear interpolation we cannot use, and the strain energy, if you compare the strain energies, then you will find out that essentially it will lock, or it will mesh will lock in terms of static means based on the H/L ratio, your finite element solution will give a garbage value as you goes to thin beam limit. So this is the reason for mesh locking. One of the main how to alleviate this locking, one of the method we have studied is that reduced integration method, where actually we nullify the contribution of the shear strain energy from the your potential energy part. So that means this by integrating this shear strain energy, if I integrate with lower order polynomial, then actually we can neglect this thing for reduced for the thin beam limit, and then if you neglect this thing, naturally UB will pop up and the bending contribution or the flexure contribution will be dominating mode. So this is one reason. Now in case of 2D element, so for instance we have studied the very simple element which is 4-noded bending element or 4-noded bilinear element. So here if you look, then let us see a simple example with the 4-noded element. Then let us visualize it, what happens, and we'll find out why it is actually happening. So for instance, let us consider a cantilever beam problem. So this problem I have taken from the Timoshenko and Goodyear's Theory of Elasticity book. This is a very well-known book. So now if this problem will have the so from the stress function approach we can find out the exact solution, which is U and V. So this is a two-dimensional beam, so plane stress assumption is again applicable. That means there is no sigma y, so that means sigma y will be 0, and then your only sigma x will be there, so there will be no shear stress also. So all those shear strains will not also be there. So these thing we have taken. So this is the exact solution. Now the same problem, if I just change my A by L ratio, that means the thickness by length ratio, how finite element mesh is behaving, let us look first. So first let us see that the first figure, which is essentially a thick cantilever beam, that means A by L ratio is 0.15, so basically the thickness is 0.3, and then if I just plot the finite element solution and the analytical solution in the previous slides, so you will see that finite element solution is almost matching with the analytical solution. So on the other hand, if you just take the aspect ratio little less, or the A by L ratio is 10 times less, that is 0.015, that means that if I increase the length of the beam and then still if I keep the 0.3 thickness, then my aspect ratio will go down. So that means if I do that, then if you will see that the analytical solution doesn't match with the deformed mesh. Or the deformed solution or the finite element solution. So that means which is shown in color of red. So in case of a thick beam, you see that this is absolutely matching, or it is reasonable to approximate. But if you go for thin beam limit, or if you just decrease the aspect ratio, your finite element solution and analytical solution is not correct. And naturally this is a problem where we can find out that this where we can find out that this problem actually we know the analytical solution, so that's why we know that it is not correct. But in case where we don't know analytical solution, if I do not know that this element locks essentially, then our approximate solution will be red mesh, which is incorrect. So that's why it is important to know that why this 4-noded element cannot be used with a full integration, for instance, for the thin beam limit, or why this element has some specific bending behavior. So let us see that. So to do that, let us again let us check what happens. So let us consider a very simple element. Now let us consider a 2D bilinear element, which is your simply under pure bending. So let us consider a simple bilinear element, which is 4-noded element. So all we know that what is the 4-noded element. So I have also the picture for this. I will insert it. Let me insert that picture, then you will understand properly. So okay, so so let us see this image. So here what is happening is that I have considered a simple bilinear element, that is 1, 2, 3, 4 4-noded bilinear element. We all know what is the shape function for this. So if I just take, this is 2a, that is node 1 to that means the length of the element is 2a and height is 2b, then the shape function, that is ni, is simple. I am just writing in terms of xy coordinate. This is valid for the local coordinate, that is xi eta system also. So a minus plus x plus b minus plus y by 4ab. Now if this element, if I give a pure bending, then what will happen? This element will behave like this. So it will be just doing this, right? So let me draw it again. So what will happen to this element? That it will just bend like this. Why it will bend like this? Because it cannot represents the behavior, pure bending behavior. So why? Because it's a bilinear element. So now if this element it will represent, so suppose this displacement is u bar, and naturally this will be u bar. So and this will be also u bar. So and this will be also u bar. So now while the pure bending will behave like this, the second figure, the pure bending problem will behave like this. So this will introduce another problem in this element, because this will create a spurious shear energy in this element. Let us look what happens. So if I just do this, then I can easily find out what is my strains and exact strains also we know. So for instance, for the element that is giving the moment m, then under pure bending, so what will happen? So u bar is nothing but my theta. If I take theta small, then theta by 2 into b. So that is my u bar, and so my ux, u of xy, if I write for this element, that is minus xy by ab into u bar. So that means if I substitute u bar, then that is my minus xy theta by 2a. Right now, v is naturally 0 for this element, because this element cannot go up during. So that means if I have a square and then if I give the pure bending, then this mode, there is no way to represent this particular bending mode for the bilinear element. If you remember the bilinear interpolation function, how we derived is that u we approximated as a0 plus a1x plus b1y plus c1 xy, and v is similar a0 or let us say, let us give some different constants, a0 plus a1x plus a2y plus a3xy, and b0 plus b1x plus b2y plus b3xy. So while x keeping x constant, it will represents only linear term. So there is no way that it can represents the bending deformation, bending mode, or this curvature. It is no way it can represents. So that's why the v deformation will be essentially 0. On the other hand, if I have a pure bending, then v deformation is not 0. Essentially, u deformation, if I write for the exact case, then what will happen is that u of xy is essentially minus xy by 2a into theta b. Now theta b I am using here now, but there will be a v. So v of xy, this is non-zero for the exact case, because naturally these fibers will go up, and on the other hand, here in the approximation, element approximation, these fibers will not go up because it cannot represent the quadratic behavior of this curvature. Now that's why it is called bilinear element. So only xy variation is there in the displacement representation. Now that if you write the u, so that is minus u, and if I write the v, then that is minus 1 minus x squared by a square into your a by 2b into your theta b by 2 into b plus or minus nu will be there because of the Poisson's ratio effect. Nu will be there 1 minus y squared by b square into your b by 2a into your theta b by 2 into b. So this will be the actual displacement, while v displacement is actually 0 here. Now similarly, if I compute my strains for this approximation and the exact, so my strains will be epsilon xx will be your minus theta y by 2a, and epsilon yy, that will be 0, and gamma xy, which is shear strain, which will be non-zero, which is minus theta x by 2a. But for the exact case, so this is my exact case, so and this is my approximate case. Now here u bar is essentially, if I use this is u bar, so that means your u bar is actually theta b into b by 2. Now the strains here, the epsilon xx is similarly, the epsilon xx remains same because if I assume theta b and theta are same, then epsilon xx remains same, but epsilon yy, which is actually nu into epsilon yy, epsilon xx, that is requirement from the plane stress assumption. If you remember that sigma x, sigma y must be 0. So then this has to be there. So it is essentially, if the Poisson's ratio, that is nu, if Poisson's ratio goes to 0, then only it is matching with the approximate thing. But again, gamma xy, which is actually 0, but it is not 0 here. Now if I write the stresses, again stresses are plane stress assumption, which is E into epsilon xx. Here you cannot write this because from the plane stress assumption it has to come from. So the plane stress, if I write the plane stress assumption, that is sigma xx, sigma yy, sigma xy, then your E by 1 minus nu squared, then it will be 1 mu 1 0 0 0 0 1 minus nu by 2 into your epsilon xx, epsilon yy, and gamma xy, right? So this from this I can find out the strains for exact and as well as for the approximation. Now with these strains and stresses, if I calculate the strain energies, what happens to the strain energy? Now let us look for the strain energy. Let us calculate the exact strain energy first. So let us calculate U exact. You see the strains, strain energies, even though here if epsilon yy is nu epsilon xx, and if I substitute that, then naturally sigma yy is 0 here and sigma xy is also 0 here. So if I write my strain energy, it is integral v sigma transpose epsilon. So this is my sigma vector and this is my epsilon vector. So now if I write this, then only epsilon xx term will be there. So basically if I write for this particular element, then what will happen? That will happen as half integral minus h to h by 2, that is thickness term, h by 2 to plus h by 2, minus b to plus b, minus a to plus a, then only term, that is e into epsilon xx whole square dx dy dz. So now if I just so this is again epsilon xx is independent of z, so so I can just write it h by 2, that is thickness, so minus b to plus b, minus a to plus a, then e into your epsilon xx is your theta b y square by 2a, theta b square, and this I can write 4a square. So 4a square dx dy, right? Now if I integrate over minus a to plus a and minus b to plus a, this integration comes as this EBH theta b square by 6a. this integration. Now similarly here the strain energy, if I write my strain energy here, then what will happen to this strain energy? That is u is half of again integral minus let us consider v, that is sigma transpose epsilon dv. Now here if I compute the stresses, I have epsilon yy 0, so and epsilon gamma xy is minus theta x. So if I multiply, so then what will happen is my strain energy will be half of integral E minus E by 1 minus nu square into epsilon x square, because this is will be there, so this is not there. Since epsilon yy is there for Poisson's ratios, then non-zero Poisson's ratios, then this term will be there, and then the sigma xy term will be there. So this is dx dy dz, the volume integral. So 3 integrals will be there, and then again you will have half of this shear term will be there. So integrals 1 minus e by 1 minus nu square into 1 minus nu by 2 gamma xy square dx dy dz. Now if I now integrate with theta epsilon xx given and theta x is 2a, then what will happen is, remember that even though sigma y is non-zero, since epsilon y is 0, so this term will, sigma y contribution will not be there. So now if I just compute this integration, then what will happen? Let me write it again like this, that is minus h by 2 plus h by 2 and all those things. So that is eh by 1 minus nu square. So that is minus b2 plus b minus a2 plus a, then theta square y square by 4a square dx dy plus half, that is e into 1 minus nu square into h by 2 into 1 minus nu by 2 integral minus b to plus b minus a to plus a, then theta x square by 4a square dx dy. Now if I compute these integrals, then this will look like this, this eh b cube theta square by 6a into 1 minus nu square plus here e by 1 minus nu square into abh 1 minus nu by 12 into theta square. So this is my u exact, and let us say u approximate. Now if I compare these two strain energy, or if I exactly find out the ratio between u approximate or the element by u exact, what happens? So if I do that, that is that is eh b cube theta square by 6a 1 minus nu square plus e into 1 minus nu square into abh 1 minus nu by 12 into theta square divided by this, that is my ebh cube theta b squared by 6a. So if I take this thing, if I manipulate or simplify it, then theta square by theta b square, that is 1 by 1 plus nu into 1 by 1 minus nu plus half of a by b whole square. This is my U approximation by U exact. So that means if I choose different, if I choose same deformation, that is theta and theta b is same, that means I need moment m by m ratio. If I that means m is the approximate moment and mb is your exact moment required to have theta b deformation. You need mb for theta b and m for theta. Now if I keep my theta, that is deformation same, that is theta and theta b equal, then you need this, in this ratio the moment should be given. So that means this is actually m by mb ratio is actually 1 by 1 plus nu into 1 by 1 minus nu plus half of a by b whole square. And this is purely due to this term, this shear spurious shear term acting on the spurious shear term developed in the four-noded bilinear element. So this spurious energy term is actually contributing this shear, and this is known as the parasitic shear. Because of this, this element behaves, even if you see that for Poisson's ratio 0, then a by b ratio, if it goes to large, if a by b ratio is large, then that means your approximating energy, strain energy approximation will be very large. So that means, and this is due to, mainly due to the spurious shear energy term. So that's why the previous case, what I have shown here, that when you have a by L ratio is less, that is thickness, that means the a by L ratio means aspect ratio, that means element, if I have the a by b ratio, that means a by L ratio is essentially here. So this ratio, if it is less, then the mesh will lock because of the spurious shear energy developed due to this discretization or this particular element. This will create the locking. So similar way that we discussed for the previous case for the Timoshenko beam, we can also impose, or we can also use reduced integration technique or selective reduced integration technique, where the shear term in the stiffness matrix we can use 1-point quadrature rule, and for the bending term we can use 2x2 quadrature rule, that is the 4-point. So if I do that, then I will be integrating bending modes actually, but shear stiffness I will be neglecting shear stiffness. So that will give me the better result compared to full integration. So that's why, because of this spurious shear, which is known as the parasitic shear, so this mesh is lock. This mesh will give the very that means the deformation or the deformed solution or the finite element solution will be not accurate compared to the exact results. So I think I have explained what is essentially the shear locking and why it is occurring. The main reason is this, that when you have a lower order element specifically, then you have generated a spurious shear energy mode or the spurious shear strains are generated in that element, and this creates an additional energy when the thickness of the element goes to, or the aspect ratio of the element becomes less, or the aspect ratio becomes high. So then this will create actually your higher shear energy. So this is what is called shear locking. So now let us, in the next class, let us see how we can alleviate this shear locking. Thank you.